Hello, 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 hello. We are live once again. Once again, indeed, we're live. We're live, we're live, we're live. This is not a test. This is not a drill. This is not a premiere. This is not a short. Indeed, we're live and we're waiting for you to join. Hopefully, I see many of you old friends as well as meet many new friends tonight. Today, I guess it is the daytime actually now. Today, in this live, if you're seeing this as a video upload later on though, thank you so much. Thank you for your likes, comments, shares, subscribes. Many thanks to you. Many thanks to you. Hello, El Challen. El Challen, we are most grateful for your support. How are you doing? El Challen 005 has says cha cha chow with a number of fire emojis. Love it. How are you doing? I'm once again on the porch and doing a porch live and matching the greenery around me with the green dress, same one. This has become my morning green dress. And then I'm having my coffee now. I just had some cereal and then I'm gonna go shower, get dressed, and do other things throughout the day. But I wanted to start with a live and to say hello to everybody and do a little bit of a Big Bang chat. Oh, I have an eye booger. Too bad. Too bad. So sad. El Jalan, thank you for being here and thank you for liking. Once more people join, I would love one of your messages that urges people to like the live. Thank you so much. How is everything else going on? How is everything else going, El Challen? So, I tried to talk about the origin of the universe yesterday, but indeed, it was a little bit interrupted and disrupted by the construction around me. And so today I'm hoping to catch many of you and continue that chat. But if you have a question on cosmology, astronomy, astrophysics, or physics, this is also a great time to ask that. I believe I was answering somebody's questions actually yesterday that led to the discussion of yesterday. And if you caught that yesterday, then thank you so much. Indeed, we are delighted that you were able to make it. Thank you, thank you, thank you. Hello, Faze. Hi, Faze. How are you doing? Hello, El Challen. Hello, Faze. Things are good. Here's the bamboo tree behind me. Here's another. Ooh, part of that thing that's behind me is sort of an IV that is growing. I'm actually quite in awe of this IV that is growing on the decorative wall here and going straight up. And so those are the things that are behind me. And of course, this is my face with my green dress on, which matches the plants. Hello, El Challen. Hello, Faze. Faze said great. Hello, Connor. Connor is a new friend. Hello, Connor Cheatham. Connor says hi. Hi, Connor. How are you doing? If you're new in the live, if you've never been on the lives before and want to say something, feel free. I will shout you out. I will read your chat message and read your comments and say your username. So have fun. Osibin says, what them? Oh my goodness. Well, Osibin, I was going to read your message, but indeed, it is a rather. There you go. The mod is here. Hello, Doro. Thank you so much. Thank you for being here. Thank you for joining Doro Madness. El Challen says, green is definitely your color. Thank you. Thank you, El Challen. Thank you, Doro. Now, Seth. It's been a hot second. Now, Seth says, hi, how are you, my friend? Well, now, Seth, how come you're never on the lives anymore? I'm seeing you after ages. What's up with that? How is everything now, Sat? How is Asia? Oh, I forgot to say good afternoon, good morning, good evening, good night to all the continents: Asia, Europe, South America, North America, Africa, Antarctica, Australia, New Zealand. I know Australia and New Zealand are part of the same-ish continent, but just saying. Is your second toe longer than your big toe? Let me see. Um, they're about the same height. I mean, the bigger toe is bigger, overall size, but I think the second toe and the big toe are about the same. Show you. Jed Jensen, aren't you being a little bit too much pushing your luck? This is not the type of service that I provide on this channel, but I suppose one can take chances. French Toast in Texas says hi. Hello, French Toast. Jed Jensen wants to see feet. Now Sats is like done. Long time meet you. How's your morning? It's going fantastic. I'm outside on the porch. It's rather amazing. The breeze is flowing. There's a water fountain thing over there that is dropping water into a pond utilizing gravity. It's actually quite fantastic. It's nice. There's a lot of greenery around me, and it's peaceful and lovely. Thank you, French Toast. Thank you for being here. Thank you for liking. Can we get 10 likes? Where's the message about the likes, Doru or El Challen, so that I can pin it? Of course. Welcome, French Toast. Welcome, everybody. I heard if a man's toe is smaller compared to the next one, the person will be submissive. What's special today? Well, we will be talking about the Big Bang. It's fresh, a little rainy, but perfect. It is fresh. Yes, it's fresh. That's for sure. The outside is extremely fresh. The breeze is flowing. I think it's going to rain tomorrow, but for now it's quite nice. Where did you hear that? Says Doro. Let's get 20 likes. Yes, can we get 20 likes? It's a Mexican saying that explains a lot. Well, what do you have against Mexican sayings, Doro? This is coffee. This is coffee. I ate some cereal. The cereal I just ate is called Fruity Pebbles with milk. So I already had that in the balcony. Then I went inside and I made my coffee. Nescafe with lactose-free whole milk. Then I'm outside drinking it, and I'm gonna read to you about the Big Bang really soon here. I love both. What's your favorite coffee brand? Nescafe. Nestle, whatever, Nestle dark roast. Actually, the one that's imported from India is my even more favorite. The same type of coffee, when imported from India, has a slightly more stronger taste. I know that because I've tried various kinds, and I go to an Indian grocery store in Boston where I buy the coffee sometimes from there, sometimes from a regular store, and the Indian one is better. For me, anyways. Coffee, I mean, makes sense. This is basically 5 a.m. for you. True. This is 5 a.m. for me. What do you mean? It's not 5 a.m. This is probably I mean, it's still early morning for me. Yeah. It's an early time during the day. Very early. Very, very early. It is, I've been up for over an hour or so. So indeed, I'm still waking up very early. Very. I don't have the name, but my favorite comes in a yellow container, kind of strong. Yellow container, kind of strong. Okay. Is a Mexican gooner. Hello, Rose. How are you today? How are you doing? It's 11:10 a.m. here. Okay, so you're an hour behind. Central, maybe? Rose, you aren't allowed to troll. You go crying to Doro for help. You know, there is some truth to that, Grimme. There is some truth to that. There is. Poor Grimme, he goes back to his boss when there is trouble afoot. Coffee cup? Thank you. I'll tell them. It's not exactly mine. I'm visiting, so I'll tell the people. I'll tell the people that their coffee cup is nice. I'm in fact Rose's boss, though. Don't ever forget that, Rose. Background place is super. I know, right? Look at that plant. Look at this plant. Look at the surroundings. Okay, you know what? Thank you. Now I'm gonna read about the Big Bang. Okay, so we have been talking about the book Brief History of Time, and currently we're on the chapter where Stephen Hawking is going to talk about the origin of the universe. I have to go eat breakfast and work out. And why can't you bring the live with you? French toast. We request that you bring this live with you to breakfast and work out. I don't mess around with her because she called you last time. Then you started to threaten me by blocking me. For some Americans who don't believe in freedom of speech. Did I call him? I didn't call him. Oh, Rose. I see. I see what's going on. Rose called him. Faye says you should write a book. Thank you. I certainly will. Do you want the book to be on cosmology? Because that's what I want to write a book on. My next book. Well, I have a number of books planned. I have around 20 books planned. But, so you never know which book will be coming out next. But, thank you for the encouragement. What are you on about? Okay, Doro, I think I get it. He's talking about Rose calling you, not me. Thank God. I don't have Doro's number, but Rose does. Hey, that's the place, guys. I showed it last time as well. I was gonna say last night, but it was actually yesterday morning. Yesterday morning. Okay, okay. Are you guys ready? I really like the ivy behind me. It's not that deep. True. Nice pond. Does it have fish? I don't think so. I don't think it has fish. But thank you. We'll never have my phone number. Rose just texts me when it's funny. It's not that deep. True. They have a non-deep connection. What books have you written? Thank you. Welcome. Well, I do have a number of books, a few books already, and one of them is called How to PhD, the Graduate School Handbook. If you're very interested, then it is available on Amazon, or you can also read my blog, howtophd.org. Okay, next we will talk about the origin and the fate of the universe and get that going. Okay, thank you so much for being here on this live. Thank you so much for liking the live. Thank you for your comments and chat messages. I will read them intermittently in between. Intermittently in between, okay? And you guys keep on keeping on. Keep on with the comments and the chats. Can we get 10 likes? And then can we get 20 likes? Thank you. Einstein's general theory of relativity on its own predicted that space-time began at the Big Bang singularity and would come to an end either at the Big Crunch singularity if the whole universe recollapsed. Is Stephen here? Stephen, I see you. Stephen, I see you. You can't hide. Thank you for coming. Or at a singularity inside a black hole if a local region, such as a star, were to collapse. Any matter that fell into the hole would be destroyed at the singularity, and only the gravitational effect of its mass would continue to be felt outside. On the other hand, when quantum effects were taken into account, it seemed that the mass or energy of the matter would eventually be returned to the rest of the universe, and that the black hole, along with any singularity inside it, would evaporate away and finally disappear. This is because we talked about black holes having sort of a temperature and quantum effects allowing it to basically emit particles sometimes. And this is, of course, Stephen Hawking's work during his PhD that he almost didn't do because he was very sick and thought he wouldn't live long enough to finish one, but then he ended up having to finish one. But in general, just as a reminder, we've talked about black holes both from a classic point of view, relativity and singularity, etc., and also sort of a quantum point of view. So when you mix the two, that's what we've been kind of talking about for the past few lives and clips, is that when you mix general relativity and quantum mechanics, you get a treatment such as this Hawking radiation thing that we're learning about. And Stephen Hawking was, I think, the first one to kind of notably do that. So that's where sort of the special part of this lies. Hello, Stephen. Spears. So on the other hand, when quantum effects were taken into account, it seemed that the mass or energy of the matter would eventually be returned to the rest of the universe, and that the black hole, along with any singularity inside it, would evaporate away and finally disappear. Could quantum mechanics have an equally dramatic effect on the Big Bang and Big Crunch singularities? What really happens during the very early or late stages of the universe when gravitational fields are so strong that quantum effects cannot be ignored? Does the universe, in fact, have a beginning or an end? And if so, what are they like? Throughout the 1970s, I had been mainly studying black holes. That is Stephen Hawking. But in 1981, my interest in questions about the origin and fate of the universe was reawakened when I attended a conference on cosmology organized by the Jesuits in the Vatican. The Catholic Church had made a bad mistake with Galileo when it tried to lay down the law on a question of science, declaring that the sun went around the earth. Now, centuries later, it had decided to invite a number of experts to advise it on cosmology. At the end of the conference, the participants were granted an audience with the Pope. He told us that it was all right to study the evolution of the universe after the Big Bang, but we should not inquire into the Big Bang itself, because that was the moment of creation and therefore the work of God. So a little bit of spirituality mixed with physics here. I was glad then that he did not know the subject of the talk I had just given at the conference, the possibility that space-time was finite but had no boundary, which means that it had no beginning, no moment of creation. I had no desire to share the fate of Galileo, with whom I feel a strong sense of identity, partly because of the coincidence of having been born exactly 300 years after his death. Oh, I see. Thank you, Doro. Thank you, Stephen. Thank you, everybody. In order to explain the ideas that I and other people have had about how quantum mechanics may affect the origin and fate of the universe, it is necessary first to understand the generally accepted history of the universe according to what is known as the hot Big Bang model. Love the bird sounds. This assumes that the universe is described by a Friedman model. So remember, Friedman was the first one who kind of took general relativity at face value and did the math to get an expanding universe worked out. So, described by a Friedman model right back to the Big Bang. In such models, one finds that as the universe expands, any matter or radiation in it gets cooler. When the universe doubles in size, its temperature falls by half. Since temperature is simply a measure of the average energy or speed of the particles, this cooling of the universe would have a major effect on the matter in it. So temperature is average. Temperature is very representative of the average sort of things that are going on, movements, speeds, and energy of particles. All those things taken together on average is basically represented by something like a temperature. So this is cool. Since temperature is simply a measure of the average energy or speed of the particles, this cooling of the universe would have a major effect on the matter in it. If the universe doubles in size, the temperature will go to half. At very high temperatures, particles would be moving around so fast that they could escape any attraction toward each other due to nuclear or electromagnetic forces. But as they cooled off, one would expect particles that attract each other to start to clump together. Moreover, even the types of particles that exist in the universe would depend on the temperature. At high enough temperatures, particles have so much energy that whenever they collide, many different particle-antiparticle pairs would be produced. And although some of these particles would annihilate on hitting antiparticles, they would be produced more rapidly than they could annihilate. At lower temperatures, however, when colliding particles have less energy, particle-antiparticle pairs would be produced less quickly, and annihilation would become faster than production. So once more, at lower temperatures, however, when colliding particles have less energy, particle-antiparticle pairs would be produced less quickly, and annihilation would become faster than production. So if the production is more, then only so much can annihilate. If the production is less, then annihilation can actually dominate. Kittens all day. At the Big Bang itself, the universe is thought to have had zero size. So there we go. Basically, we're thinking that the universe is expanding from sort of this Big Bang or zero size state to where it is now. And either, depending on the expansion rate, it could either end up slowing down the expansion, that is, and ending up in a big crunch, which is a contracted universe, or it could keep expanding at a steady state, or it could expand at a rate just fast enough to avoid the big crunch, but not so fast. Okay, at the Big Bang itself, the universe is thought to have had zero size, and so to have been infinitely hot. So the universe was very hot, dense, Lots of things happening. Remember the angry photons hitting everybody and making, you know, nothing be able to cool down and become stable. That was what the beginning of the universe was like. And we've kind of talked about this in other contexts. We've talked about this from the other book that we reference sometimes. It's called Modern Cosmology, Scott Dodelson's book. So we've talked about the Big Bang nucleosynthesis, and sort of what has gone on during that time. So some of this is sort of a review, and also we get to hear Stephen Hawking's perspective. So that's where this is useful, because it's good to hear it again. But as you know, that the beginning of the universe was radiation dominated, and photons were like king of jungle. It was hot, dense, energetic. Photons would hit everything and not let neutral atoms form, for example, and things like that. So again, at the Big Bang itself, the universe is thought to have had zero size, and so to have been infinitely hot. But as the universe expanded, the temperature of the radiation decreased. So because the universe now expanded, temperature decreased. 1 second after the Big Bang, it would have fallen to about 10,000 million degrees. 10,000 million degrees. This is about 1,000 times the temperature at the center of the sun. But temperatures as high as this are reached in hydrogen bomb explosions. So basically, about a second after the Big Bang, the universe was sort of like a hydrogen bomb explosion. Hello. Thank you for being here, everybody. Can we get 10 likes? At this time, the universe would have contained mostly photons, electrons, and neutrinos. It's really photons, electrons, positrons, neutrinos. We've talked about how the photons, electrons, positrons were constantly interacting with each other, and they were also going to be interacting with the neutrinos, but at some point, actually, the expansion rate was bigger than the interaction rate with neutrinos, and the neutrinos had a bit of a breakup with the photon, electron, and positron soup. So maybe he'll talk about that, we'll see. At this time, the universe would have contained mostly photons, electrons, and neutrinos, extremely light particles that are affected only by the weak force and gravity. They're also affected by electromagnetism. I don't know why. Oh, he means neutrinos. I was going to say photons, electrons, and positrons are affected by electromagnetism as well. But I think he means that neutrinos are extremely light particles that are only affected by gravitation and the weak nuclear force. Okay, I think that's what he means. Oh, and they're antiparticles, together with some protons and neutrons. Got it. So he's saying the same thing that we know already, that the beginning of the universe basically had photons, electrons, positrons, neutrinos, antineutrinos. And small amounts of protons and neutrons. We knew that. As the universe continued to expand and the temperature to drop, as the universe continues to expand and the temperature continues to drop, after the Big Bang, that is, the rate at which electron-anti-electron pairs were being produced in collisions would have fallen below the rate at which they were being destroyed by annihilation. So once again, the rate at which electron-anti-electron pairs were being produced in collisions would have fallen below the rate at which they were being destroyed by annihilation. So most of the electrons and anti-electrons would have annihilated with each other to produce more photons, leaving only a few electrons left over. The neutrinos and antineutrinos, however, would not have annihilated with each other, because these particles interact with themselves and with other particles only very weakly. So they should still be around today. Isn't that so cool? If we could observe them, it would provide a good test of this picture of a very hot early stage of the universe. Unfortunately, their energies nowadays would be too low for us to observe them directly. However, if neutrinos are not massless but have a small mass of their own, as suggested by some recent experiments, we might be able to detect them indirectly. They could be a form of dark matter, like that mentioned earlier, with sufficient gravitational attraction to stop the expansion of the universe and cause it to collapse again. So, as we know, neutrinos have been considered as a dark matter candidate, but so far we don't think that they account for all of the dark matter that we need. Okay, that we seem to have. But here, Stephen Hawking is kind of considering them in that sense, just like others have. So, because this book was written in 1988 for the first time, and then the 10-year anniversary edition came out, which is this one. So, by the time it's like 1998 is this stuff we're talking about is current as of that. So some of the things have been updated since, and one of those things is that neutrinos were definitely considered to be a candidate for dark matter. But where we stand today, we don't think that that they explain all of the dark matter. How close are we to the moment of the Big Bang? I forget now. It's the same as the age of the universe, which is around 13.6 billion years. I don't smoke. So he mentions about those neutrinos shortly after the Big Bang, who would have interacted kind of differently and not annihilated as much, because the neutrinos only interact through the weak nuclear force. So it's not the same as photons, electrons, and positrons. So those particles, interactions, and fates, and what happened to them is a little bit different than the neutrino. And remember that the expansion rate basically also makes things cool down and affects those interactions. And the way in which that affected neutrinos is that the neutrinos had a bit of a breakup with the photon, electron, positron soup. Okay, and the neutrinos had a slightly different trajectory of their fate, basically. Gang Bang Queen. Hi, Hans. Only one who smokes, I think, is Reese. Yeah, I don't know where Reese is. I should have worded it right. How soon after the Big Bang did stars and galaxies start to form? I see. The first stars, you know what? I don't know. I have to check. I forget. Like, are you asking like which giga year? I can't remember. So I know that the CMB, the cosmic microwave background photon radiation, is from when the universe was only 300,000 years old. So 300,000 years old is still considered very early universe. So I'm guessing that the first stars and galaxies were after that. But I don't know exactly. I have to check. Where was space? Where was space at the beginning of the universe? So space-time is part of the universe. So space-time was just whatever the universe was doing at that time. Perfect. Thank you. Hi, Shakuni. Hi, Shakuni Mama says hello, Andre. Hello, Shakuni. How is everything going? How is Orissa? Shakuni is from India, a state called Orissa, which was a neighboring state of mine. Yeah, so all the important sort of numbers I know is we just talked about the 1 second after the Big Bang. Then the next notable year is the 300,000 years old universe, which gave us the CMB, cosmic microwave background photons. Um, but the first stars, like, because the first generation stars were super duper metal poor. They're basically just hydrogen and helium blobs and whatnot, and then they would have um, died to make the next generation and the next and the next. So yeah. Oh, you still remember? Of course, I remember everything. I have a very good memory. I'm glad to meet you. Thank you. I do remember most things. Good memory. How was the protons and neutrons created back then? Yeah, that's a great point. So the Big Bang actually made a little bit of the baryons. The first baryons, which is protons and neutrons, were made by the Big Bang. So what that means is that the Big Bang is responsible for making a little bit of hydrogen and even smaller amounts of helium and very trace amounts of lithium. So because we got hydrogen and a bit of helium in the Big Bang, we are able to make, like, that's basically the matter, right? So we were able to make stars and stuff out of that. And then everything else, like all the heavier elements, are made in stars. So you don't get beryllium, boron, you know, nitrogen, oxygen, all these things were made in stars, living and dying. So पानी की चल चल आवाज आ रही है. Yes, there is a little pond and fountain right here. Yeah, they just fixed the fountain in the pond. So there's a little pond here. I can show you in a bit. It's like a massage parlor with the pond and with the falling water. So basically all of that is to say that protons and neutrons, like hydrogen is basically a proton, right? Depending on the isotope of hydrogen, you may have a neutron in there. But those things, protons and neutrons, enough to call it hydrogen, because hydrogen is a very simple element with just the one proton. If you increase the number of protons, it would be helium, right? 2 protons would be helium. But if you increase the number of neutrons, you get a different isotope of the same element, hydrogen. So the Big Bang made hydrogen and a little bit of helium and very, very trace amounts of lithium. So much so that if I forgot to mention it, it would be fine. So that's how we got hydrogen. And guess what? Even now, the most abundant element in the universe is still hydrogen. So stars were made from just that hydrogen and helium, and later on, as stars have their own life cycles that we talk about in various lives, the stars made the heavier elements. Like all of the rest of the periodic table is made in stars. Okay. आपका काम कैसा चल रहा है? Hopefully good. Thank you for the questions. I'll keep going for now. Okay, so it looks like during Stephen Hawking's time, they maybe did not fully understand neutrinos. I mean that's normal, that's natural. Neutrinos are extremely low mass particles, so for a while people thought that they might not have any mass. So depending on if the neutrino has mass or not, that kind of changes certain things. And I think Stephen Hawking, while writing this book, some of those things were up in the air. And he's considering neutrinos as a candidate for dark matter, which is fine because that's what people did in the beginning. You know, finding that there is some extra matter that we still have to account for, that we can't see, because it doesn't interact with photons, it doesn't interact with electromagnetism. And then also realizing that neutrinos interact through gravitation and weak nuclear force only, it's a natural candidate for dark matter. But then we found that neutrinos are probably too low mass to really account for all of the dark matter that we're seeing, or not seeing, feeling, measuring. Because seeing is what we can't do. Seeing requires interaction with photons, which dark matter doesn't do. So So then we had to kind of move on from neutrinos and think about what else they could be. Exact location of where? Where did the Big Bang take place? Oh gosh. So, where did the Big Bang take place? So it's a very good question. But basically, the universe has expanded from there. And it's pretty much kind of infinite. So at this point, going back to like exactly where the Big Bang happened, like sort of geographically like that is because remember, the Big Bang is a singularity. It's not exactly sort of a normal physical location, if that makes sense. But that is a good question, something to think about. About 100 seconds after the Big Bang. So now we're at 100 seconds after the Big Bang. Stephen Hawking talking about it. About 100 seconds after the Big Bang, the temperature would have fallen to 1,000 million degrees. 1,000 million degrees. The temperature inside the hottest stars. At this temperature, protons and neutrons would no longer have sufficient energy to escape the attraction of the strong nuclear force and would have started to combine together to produce the nuclei of atoms of deuterium, which is heavy hydrogen, which contain one proton and one neutron. So this is what I meant, that the Big Bang basically made some protons and neutrons, but can we really call them elements before they start to do this strong nuclear force type of thing? Some level of cooling from the Big Bang is necessary before you can really say that we made hydrogen. We made some neutrons and protons in the Big Bang, but then after some cooling is when we can say, oh, this is hydrogen or this is deuterium, because those protons and neutrons have to be attractive towards each other enough to make a nucleus type thing. Forget the electron, because having the electron in the atom would make it a neutral atom. But even for the neutron and proton to be close enough together to call it a nucleus of deuterium would mean that the strong nuclear force is working, which it doesn't have to if it's too hot. So once again, when it became 1,000 million degrees, the temperature inside the hottest stars, which is the same as the temperature inside the hottest stars, at this temperature, protons and neutrons would no longer have sufficient energy to escape the attraction of the strong nuclear force and would have started to combine together to produce the nuclei of atoms of deuterium. So again, the stuff that makes everything is shaking, sorry, the table is very easily shook. The stuff that keeps the nucleons together, meaning the stuff inside the nucleus, protons, neutrons, etc. Well, no etc. Just protons and neutrons are generally inside the nucleus, right? The force that keeps protons and neutrons together, or neutrons and neutrons together, or protons and protons together, is the strong nuclear force. Because actually, those things don't have to stay together. Those things don't have to stay together. They can repel each other because of electromagnetism. But what keeps them together in a nucleus of any element is the strong nuclear force. But if things are too hot, like in the very beginning of the universe, it's too hot. If it's too hot and things have too much energy, then it will surpass the strong nuclear force and not be together. And so then we would just call them neutrons and protons. We would not say, oh, we formed a nucleus and we made deuterium or we made hydrogen, right? So deuterium was important in those early days of I can't even say early days, in those early moments of the universe. The proton neutron coming together, making a deuterium, is something that we are able to still measure, actually. What is a singularity composed of? So in the case of black holes, we say a point of infinite density is what the, so remember how when we talked about black holes, basically at some point the star has collapsed to such a compressed version where it has infinite density and the gravitational field is infinitely high. So it's purely a mathematical type of point. Like it's okay to have infinity in math, right? It's okay to, you can have singularities all day long in mathematics. But people actually thought that this was quite ridiculous and black holes could not truly exist, right? Like this, something collapsing, stars, right? Stars, when they die, they collapse to various things. It could be white dwarfs, neutron stars, or black holes. But in the case of black holes, the very massive stars are compressing down or collapsing down and becoming a compressed or compact object to the point of compression where it has infinite density and infinite a point of like too much gravitational field basically for anything to escape. I guess not too much, really so much gravitational field where even light cannot escape. That's really the definition, right? So that's an example of a singularity. That's the other type of singularity. Now the Big Bang is basically a similar thing, but the other way. So black holes came from something collapsing down to like it's almost like a this way singularity, and Big Bang is like a this way singularity. Big Bang is like a singular, it's almost like a black hole in reverse, if you will, because the universe basically has started to expand from then on. Yes, the universe is still expanding. Nothing asked if is the universe still expanding. Indeed it is. Yes, sir. Yes, ma'am. The universe is still expanding. So they're both singularities. In fact, those are the two singularities of nature that we can readily think about. And in mathematics, having a point of infinite density, having some infinite thing come out as the answer is completely okay. Ask a mathematician, they will give you infinity all the time. In physical reality, we don't really like infinity as the answer, and having some point of infinite density, what is that? They didn't like it. The mathematics for black hole existed and people didn't like it. Einstein didn't even like it, okay? It was only observation where we saw, oh my gosh, black holes are real. Then we know that, wow, okay, black holes are real. So black holes are like big star collapsing down to such a compressed version where it has infinite density, gravitational field infinitely high or very high, to the point where even light will bend and not escape. Space-time bends so much light cannot escape. Big Bang is the other way singularity. It was like this, became like this, which is the universe now, expanding from the Big Bang. So I'm not sure that anybody can explain a singularity super well, because it's actually a mathematical entity, if you will. It's not something which has a ton of physicality to it. So I'm trying, but certainly I'll keep the question in mind and try to explain it better next time or sometime. But that's what I got right now. Thank you. Thank you for 10 likes. Can we get 20? But it's those are the two singularities, and they're kind of the same, but opposite ways. This. Big Bang going from here to here. Time starts. Black holes going from here to here. Time stops. Because remember what we talked about, in a black hole, time stops. Once you've made a black hole, your time is done. It stops. You will still see the same time. I mean, you'll be dead, but if you could see the time, it would be the same time. Time will just stop. In the Big Bang, time starts. So kind of the same thing, but in reverse directions. It's almost like a video playing forwards or backwards. And right now the video is playing forwards. So if somebody asks is the universe expanding? Yes, it is. It is. Unless you fall into a black hole, your time will stop. Then you will not know that, then you won't have the same perception of the universe. If you fall into like if you go past the event horizon of a black hole, then time is not fake. Space-time are the 4 dimensions that we experience. Some people, so if you think time is fake, I mean, it's a space-time dimension, okay? There's 4 things, T, X, Y, and Z, and general relativity makes use of those 4 things, and everything is explained with that geometry of the 4 space-time. So if you don't believe in T, it's like the saying, oh, I don't believe in X, you know? Time is treated in the same way as space in that sense. It's a 4 space-time, right? Not the exact same, but similar. So some people believe in even more dimensions, right? Like string theory, superstring theory has 10 dimensions, depending on, I think it was M theory, which has 11 dimensions. So the 4 space-time is what we experience and what we can postulate and describe the universe with as a space-time thing, and gravitation being a space-time curving thing. So, you know, time is definitely a thing. If you think time has stopped, then you might be in a black hole, which is completely possible. Which is completely possible. We can keep an open mind. On a clear night, and look in the right place, you can see the Andromeda. Yes! Oh, nice. Can we see Andromeda right now? Are there protons and neutrons in ourselves? Yes, of course. We're made of protons and neutrons. Yes. Mm-hmm. Of course, we're made of carbon, water. Those are all, carbon is 6 protons and 6 neutrons. Carbon 12. Of course, we're made of protons and neutrons. So yes, I should have said that the Big Bang made compared to the number of photons, electrons and positrons, it actually made kind of fewer baryons, which is basically the term for clubbing together protons and neutrons. And then later on, those protons, neutrons making hydrogen, which is obviously the lightest, most simplest element, and then some amount of helium and lithium. That's what the Big Bang and the early universe made, and then everything else, heavier elements, were all made in stars, and then we are made of stardust, as in stuff that gets blown out to the interstellar medium once stars die and whatnot. So we, Earth and Sun and the other planets in our solar system, come from a gigantic gas cloud that condensated to make the sun and the planets, and then we came to be at some point. We're made of, you know, whatever was available on Earth, for example. And so for sure, we're made of protons and neutrons. Particularly, like, there's more chemistry involved with us. I believe it's mostly carbon, water, you know, oxygen, nitrogen, those types of things. And like ammonia is NH3, right? Oxygen is O2, water is H2O, carbon is C, sand is basically silicon dioxide, SiO2. Things are moving about. There's a breeze here. So we are made of chemical elements that are all made in stars, and the stars came from the initial elements made in the Big Bang, hydrogen, helium. So everything is just protons and neutrons. Yes. us and the universe is like one big living organism. Yes, yes, it goes through a lot of cycles, that's for sure. We do, and so does the universe. Yes, it is. And okay, we can see Andromeda between September and November, the autumn months. Oh, nice. Well, that's my birthday season. So now let's see about 100 seconds after the Big Bang, it was cool enough to make deuterium, as we found out. Steven, I remember, Steven, your birthday's in November, right? Aren't you a Scorpio? What was your birthday again? November 11 or something? Okay, at this temperature, protons and neutrons would no longer have sufficient energy to escape the attraction of the strong nuclear force and would have started to combine together to produce the nuclei of atoms of deuterium, heavy hydrogen, which contain one proton and one neutron. The deuterium nuclei would then have combined with more protons and neutrons to make helium nuclei, which contain two protons and two neutrons. So basically, I mean, yes, it is. Mine too. Yeah, November 5. Oh, good. November 5. I got it wrong a little bit. So basically, if you can make deuterium, which is a proton and a neutron, why not take two protons and two neutrons and make helium too, right? So when things have cooled down, you can start to make deuterium, you can start to make helium, some isotopes of these things, and you start to get into business, basically. Because we're made of, as you said, as you know, neutrons and protons. I mean, we won't be here if those things were not made. And basically the Big Bang, it's not like the Big Bang gave us too much, but it did give us some protons and some neutrons to ultimately, after cooling down, make deuterium and helium, and some tritium as well, tritium, and other things. So, oh no, okay, see you next time, Steven. See ya, have a great day, see you. I'm still here. Okay, so the deuterium nuclei would then have combined with more protons and neutrons to make helium nuclei, which contain two protons and two neutrons, and also some amounts of a couple of heavier elements, lithium and beryllium, but very trace amounts. Lithium and beryllium, very trace amounts. One can calculate that in the hot Big Bang model, about a quarter of the protons and neutrons would have converted into helium nuclei, along with a small amount of heavy hydrogen and other elements. The remaining neutrons would have decayed into protons, which are the nuclei of ordinary hydrogen atoms. The remaining neutrons would have decayed into protons, I see. I like zoned out for a second. But the remaining neutrons would have decayed into protons, which are the nuclei of ordinary hydrogen atoms. So basically, neutrons can decay further into protons. Because, I mean, neutrons are neutral. There are processes that basically you can take neutrons and go down to a proton. And a proton is nothing but hydrogen. So actually, and that is the most abundant element of the universe. So we did make quite a bit of hydrogen as well. Deuterium, helium, tritium, hydrogen. These were all made soon after the Big Bang. I think it's like raining a little bit, so I'm gonna stick around for a few more minutes, and take any questions and whatnot. But thank you so much, everybody, for being here, and thank you for the likes and the questions and the shares and the subscribes and the comments and chat messages. I see only 8 likes. Did people start to dislike the live? That would be quite heartbreaking. Can we get 10 likes and can we get 20 likes? Thank you so much. Thank you so much. So this picture of a hot early stage of the universe was first put forward by the scientist George Gamow in a famous paper written in 1948 with a student of his, Rolf Alpher. Gamow had quite a sense of humor. He persuaded the nuclear scientist Hans Bethe to add his name to the paper to make the list of authors Alpher, Bethe, and Gamow. alpha, beta, and gamma, like the first three letters of the Greek alphabet, alpha, beta, gamma, particularly appropriate for a paper on the beginning of the universe. In this paper, they made the remarkable prediction that radiation in the form of photons from the very hot early stages of the universe should still be around today, but with its temperature reduced to only a few degrees above absolute zero, which is minus 273 degrees Celsius. It was this radiation that Penzias and Wilson found in 1965. At the time that alpha, beta, and gamma wrote their paper, not much was known about the nuclear reactions of protons and neutrons. Predictions made for the proportions of various elements in the universe were therefore rather inaccurate, but these calculations have been repeated in the light of better knowledge and now agree very well with what we observe. It is moreover very difficult to explain in any other way why there should be so much helium in the universe. So I told you hydrogen's the most abundant element. Next one is helium. So why would there be so much helium in the universe? It's because of what the Big Bang, or soon after the Big Bang, kind of did. We are therefore fairly confident. There's a bug on my... Hello, bug. Please go away. I'm scared of bugs. Nathan! Hello! Do you see my natural surroundings? Hello, Nathan. Hello, indeed. We are therefore fairly confident that we have the right picture, at least back to about 1 second after the Big Bang. So we think we have the right picture because of these other, because of measurements we've made. We have deuterium measurements. We also know about the helium, and so that's why we think that we understand the Big Bang quite well, actually. Especially going back to about 1 second. So going back to about 1 second after the Big Bang, we think we have a pretty good idea what happened because it confirms our observations. Because it confirms our observations of what we see from those early days, from those early moments. Can't really say days. So, yeah. Within only a few hours of the Big Bang, the production of helium and other elements would have stopped. Hello, Mike D. Thank you for 10 likes. Can we get 20 likes? And after that, for the next million years or so, the universe would have just continued expanding without anything much happening. So I think we're going to get to the part where we might see when the stars and galaxies formed, maybe. Eventually, once the temperature had dropped to a few thousand degrees, because remember, as the universe is expanding, its temperature is going down, and so things will cool down enough to make more things. We'll see. Nathan, how are you doing? I love it outside. What if the universe is really the inside of the body of Christ? That is a spiritual question that I'm not sure of. Mike D, hello. Thank you for being here. Eventually, once the temperature had dropped to a few thousand degrees, and electrons and nuclei no longer had enough energy to overcome the electromagnetic attraction between them. So, if things are too hot, then electromagnetic attraction cannot take place. When things cool down enough, electromagnetic force kicks in, and nuclei and electrons will attract each other because they have opposite charges. Sorry, I've missed a couple of lives. Yes, you have. It's very sad. Did you go listen to them later on? Eventually, once the temperature had dropped to a few thousand degrees and electrons and nuclei no longer had enough energy to overcome the electromagnetic attraction between them, they would have started combining to form atoms. Okay? So remember, we cannot get atoms or neutral atoms until things cool down enough to about a few thousand degrees or so, to the point where electromagnetic force of attraction can take place between electrons and the nuclei.
Nuclei have positive charge because of protons, electrons have negative charge. Remember how the electromagnetic force, of course, is both attractive and repulsive depending on like charges or opposite charges. In this case, electrons and nuclei would be oppositely charged and therefore attractive. But this attraction means that there is electromagnetic force working, which it wasn't working when things were more hotter and crazy in the universe. So expansion had to happen, things had to cool down more for this to happen. Oh good, Nathan says, so you have checked out the lives afterwards. Thank you so much. Yeah, every live is posted under the live tab that you can go and see at any time. The universe as a whole would have continued expanding and cooling, but in regions that were slightly denser than average, the expansion would have been slowed down by the extra gravitational attraction. So this is where things will get interesting now. The universe did expand, and the universe did cool, but there will be some regions of extra density, over densities, which would have behaved a bit differently. Thank you for mentioning me in the videos. Oh, of course. Yes, I try to tag everybody that I can find the usernames of to let people know that what's coming out and such. This would eventually stop expansion in some regions and cause them to start to recollapse. As they were collapsing, the gravitational pull of matter outside these regions might start them rotating slightly. As the collapsing region got smaller, it would spin faster, just as skaters spinning on ice spin faster as they draw in their arms. So it's sort of like an angular momentum conservation. Eventually, when the region got small enough, it would be spinning fast enough to balance the attraction of gravity. And in this way, disk-like rotating galaxies were born. So millions of years after the Big Bang, it seems the first galaxies were born. Other regions which did not happen to pick up a rotation would become oval-shaped objects called elliptical galaxies. In these, somebody had asked, how soon after the Big Bang did we get the first galaxies and stars? Millions of years later is the answer. Thank you so much for asking. And can we get 20 likes? Other regions which did not have, so, as we know, galaxies are different. Because we are living currently in the current time, we already know that galaxies come in sort of these different shapes and whatnot, shapes and sizes. Galaxies are all different shapes and sizes, but broadly speaking, they're either spirals or ellipticals or irregular. Some galaxies just have a terrible shape, just no shape, just shapeless, weird, and those are called irregular galaxies. Then we have spiral galaxies like the one we live in ourselves, Milky Way. Then we also have elliptical galaxies, which are kind of like ovals. So he's talking about these ones. Other regions which did not happen to pick up a rotation would become oval-shaped objects called elliptical galaxies. In these, the region would stop collapsing because individual parts of the galaxy would be orbiting stably around its center, but the galaxy would have no overall rotation. Very interesting. As time went on, so again, millions of years after, all of that expansion kept happening, cool down kept happening. Millions of years after the Big Bang, we started to get the first galaxies. As time went on, the hydrogen and helium gas in the galaxies would break up into smaller clouds that would collapse under their own gravity. These are stars. As these contracted and the atoms within them collided with one another, the temperature of the gas would increase until eventually it became hot enough to start nuclear fusion reactions. Because as we know, what it takes to make a star is it has to have a nuclear reactor in its belly. It just has to. These would convert the hydrogen into more helium, and the heat given off would raise the pressure and so stop the clouds from contracting any further. Guess who is doing this near us? The sun. They would remain stable in this state for a long time as stars like our sun, burning hydrogen into helium and radiating the resulting energy as heat and light. More massive stars would need to be hotter to balance their stronger gravitational attraction, making the nuclear fusion reactions proceed so much more rapidly that they would use up their hydrogen in as little as 100 million years. 100 million years is not very long. Our sun is about 4 billion years old, and it's a young star. So in cosmology, giga years or a billion years is sort of the timeline for things. So 100 million, because a billion would be 1,000 million. 100 million is fast. Basically, it's like saying, "Oh my God!" Like, you know, something is going really fast. They would then contract slightly as they heated up further, would start to convert helium into heavier elements like carbon or oxygen. This, however, would not release much more energy, so a crisis would occur, as was described in the chapter on black holes. What happens next is not completely clear, but it seems likely that the central regions of the star would collapse to a very dense state, such as a neutron star or black hole. There's more understood about that process now, but when he's writing the book, maybe some of the star collapsing physics is not yet fully known. So, you know what? We're on page 124 of Brief History of Time by Stephen Hawking. We will pick this up next time because it's starting to kind of rain a little bit, and I have to get ready for lunch. So thank you so much, everybody, for joining. Thank you so much for listening. Thank you for the comments. Thank you for the shares, the likes, the subscribes. Really do appreciate it, as always. I'm glad that I've been able to kind of do these porch lives with you while traveling, and squeezing in some time with the book and with all of you guys to hang out and read and stuff. So thank you so much for being here. Once I'm back, we will go back to our night lives as per usual, but I think we'll try to always have these random other time lives as well, because it keeps it kind of fun and changing and whatnot, interesting, and I seem to catch kind of more of you different people at different times. So we will always have the night lives on. I think what we'll do, the schedule will be Monday, Tuesday, Thursday, and mostly Sunday. We will definitely have the night lives, and then, well, actually, we will probably have night lives most days, but sometimes when I'm traveling or have the time, we will also have day lives like this, because that seems to work as well. I seem to catch people at these other times as well. So thank you once again for being here. I gotta run. It's not pouring, but it's definitely raining, and I do have to get ready. So thank you so much for joining. Thank you so much for being here. Oh my God, there's something on my head, on my hair, in my hair. Things have fallen from the trees onto me. You can see the rain as well a little bit. And this has been an all-natural nature outside live. Hopefully you liked it. Thank you, everybody. Thank you so much for being here. Thank you indeed. Love you, miss you. See you so soon. What is for lunch? I don't know yet. I'm not super sure. It might be grilled cheese sandwiches or something like that. Thank you so much. Bye bye. Bye bye. Please do like, share, subscribe. Thank you, thank you, thank you, thank you, thank you, thank you. Yay. Bye. Bye.